In this video, we're going to take a look at the linked list data structure. But we're going to start our discussion off by representing a contact list. So the type of contact list you would find in your cell phone that has just a list of names and associated numbers, maybe physical addresses as well. So any information associated with that contact. For our contact list, we're only going to keep track of the first names. And initially, instead of using a linked list, which is the main data structure we're going to talk about in this video, I first wanted to talk about representing it using a vector. So initially, we'll say that we have a vector of size 6, and we have maybe 6 contacts that's able to fill up that vector. So we have maybe April is one of our contacts, we have Chris, we have, let's say, Gina, we have Mark, we have Sally, and the last one we'll have is Tom. So these are all of our contacts that we currently have, and you can imagine that maybe over time we make new friends and we need to add in new contacts. And you can see that the way we have it ordered here, we have an alphabetical ordering. So we only have the first names, but typically contacts lists will either be ordered by first name or by last name. In this case, we only have one name to deal with. So what happens whenever we have maybe a friend that we want to add, and we'll say that we have Bob up here that we just made friends with, and we're interested in adding Bob. And Bob should be going in between April and Chris. So in the case of the vector, if that's our data structure that we're using, what would have to happen is we would have to, for one, increase the size of our vector. So we can imagine maybe increasing the size of our vector by 1. And then what would happen is we would have to go about shifting all of these elements after April down by 1. So they'd have to move over by 1. So we'd have Tom shifting over, we'd have Sally shifting over, Mark, then Gina, and then Chris, so that we can actually fit Bob in here. And this may not seem like a lot of work for a computer to just shift over 5 of our contacts to make room for Bob here. But what happens is the more contacts we have, the more work we'll have to do. So the amount of work is growing in direct proportion to the number of contacts we have. Or more formally, we'd say the amount of work to do in an insertion operation is growing linearly if we're using a vector, because it requires the shifting going on. And it would be the same idea if we were trying to do a delete operation, except we'd be going in the other direction. So say we wanted to delete Gina here, we'd have to move Mark over and then move Sally over and move Tom over, and if we had additional elements, we'd have to move those over as well. So our work is dependent upon the number of contacts we have. But we can in fact reduce the amount of work for insertions, deletions, so that it's independent of the number of contacts we have. So the amount of work to perform an insertion into 6 contacts would be the same amount of work that we'd have to do an insertion into, say, 1,000,000 contacts if we were to have 1,000,000 contacts. But we cannot achieve this with the vector data structure. We have to move to a new data structure. And as you can imagine from the introduction and also the title of this video, that data structure is what we call the linked list. So let me go ahead and label our vector here, just so we can keep track of what we're looking at. So this was our vector data structure to represent our contact list. And we're going to attempt to move this vector here down a little bit so we can draw our linked list. So this linked list data structure consists of what we call nodes. So you can think of just a node as like a box. And in that box you would have all the information associated with, well, in this case, associated with a contact. So we just simply have names, our first names associated with our contacts, but if we were trying to make a real representation of a contact, we'd have a place for, first name, last name, their physical address, their telephone number, so all that information. So we'll just say that we have a node here for April. So we're going to go and replicate this same exact contact list we had down here with our vector, but now represent it with a linked list. Now the other key piece of information that you'll have associated with a node, and really what makes it a node associated with linked lists, is that we have what's called a link. So we'd have a link here, and I'm going to just represent it using an arrow here. And this particular link is capable of referring or referencing other nodes of a particular type. What I'll do now is generate nodes for Chris, Gina, Mark, Sally, and Tom so that we have a linked list structure. So now we have our linked list structure constructed, or at least a logical representation of it, and you can see that each one of our nodes that we have is linked to the node following it. So we have April linked to Chris, Chris linked to Gina, Gina linked to Mark, Mark linked to Sally, and Sally linked to Tom. So with this linked list structure, the way we go about getting from one node to another node is via these links here. We don't have what we had with the vector. So with the vector, we had these index values. Each one of these elements here were adjacent or contiguous to one another. That's not the case with the linked list. So these nodes could be very far apart in terms of where they reside in memory. So April could be 1,000 address spaces away from Chris, and Chris could be 10,000 address spaces away from Gina, whatever it may be. The way we get from one node to another node is via these links here. These links in actual implementation are pointers, so they hold addresses, and they're just holding the addresses of wherever the next node is. So we could follow these links all the way through our linked list. So that's basically how we go about traversing our linked list, is by following these pointers, these links. And we get to the very end here, and we need to have some mechanism to indicate that we're at the very end of the list. So this Tom node here is our very last node in our linked list, and we need to have his link actually referencing something to indicate that, hey, this is the end of our list. So what you typically have is some terminating value like null, which is usually represented by the value of 0. It really depends on the language that you're using, but we'd have some sort of terminating value there. So let's take a look at adding Bob here to this particular contact list that we have represented with a linked list. So I'm going to draw Bob's node down here, and we'll have Bob's link coming out of his node, and we'll have the name Bob associated with it. What's really cool about linked lists is to get Bob in the correct position, which is basically between April and Chris. The only thing that we have to do with a linked list is take April's link here and point it to Bob, and take Bob's link and point it to Chris. And that's it. That's the only work we have to do. And that's a huge advantage in comparison to what we had to do with the vector. So with the vector, we were having to shift all of this business past April down by 1. And if we would have had more elements, so in this case we only had 5 elements that we had to shift, but we could have had 10,000 elements we had to shift, or 1,000,000 elements that we had to shift. It doesn't matter in the case of the linked list. So in the linked list, we could have had 1,000,000 elements here after April, and it was still only required us changing April's link to point to Bob and Bob's link to point to Chris. So let me go ahead and update that. So we'll update what April's pointing to. So we'll say that April is now pointing to Bob here, and Bob is now going to be pointing to Chris. So let me update that one as well. And that's it. That's the only thing that's got to transpire to get Bob into the correct position. Now, that doesn't mean that everything's bad about the vector. The vector is still, a very powerful data structure. It just really comes down to what you're interested in doing, or what the operations are going to be. Whenever we're comparing the linked list versus the vector, the linked list is very good at doing insertions and deletions, because we can do insertions and deletions in a constant amount of time. So it doesn't matter how many nodes that we have in our linked list, it still takes the same amount of work, which is basically, in the case that we have here, just updating a couple of pointers. Whereas in the vector, if we have to do an insertion or deletion, then we're looking at shifting them over by 1, either to the right or to the left, depending on if it's an insertion or a deletion. So while the vector doesn't excel in terms of doing insertions and deletions, it does excel at being able to access any particular element in a constant amount of time. And what that means is we can just specify the name of our vector and a particular index value and immediately get to the contents associated with that particular element. So if we're interested in accessing the information associated with this contact Mark, we can just specify the name of the vector and the index value. Whereas in the case of the linked list, we would have to start here at April and follow these links through Bob, through Chris, through Gina, and then finally get to Mark. So it's going to take a lot more time here, and it's actually a function of the number of elements that we have. So it grows again linearly, and the amount of work that we'd have to do in order to go about maybe finding a particular thing. So in the case of the vector, we could actually employ using binary search. So with binary search, we saw that we were able to split the search space in half on every single comparison. You have no mechanism to do binary search with linked lists, because you have to start at the beginning, or you may be able to start at the end depending on what kind of linked list you have. And in the linked list that we have here, we only have a mechanism to go forward through our list. Now there is other types of linked lists called doubly linked lists, in which we could actually start maybe at the end of our linked list and traverse this way, but we would have to have links pointing in the other direction. Typically what you'll have with a linked list is, let me go ahead and draw this maybe in blue, is we'll have a pointer here to the head. If we don't have a pointer there to the head of the linked list, then we have no mechanism to actually start and get anywhere in our list. We have to have something pointing there to the head. So typically what you'll have in terms of implementation is you'll have one class that's able to implement the node itself. So the node just encapsulates the data associated with whatever we're trying to describe. In this case, we're trying to describe a contact. So again, first name, last name, address, email, phone number, whatever it may be. And then also a link to that same type of structure. So a link to a contact node. So that's what would be in a node class. And then you would have a linked list class that would consist of maybe a head pointer. You may also have a tail pointer as well. So the tail pointer would be pointing to the very last element in your list. So we may have one of those. Let me go ahead and draw one of those in. So we may have a tail pointer. And then also the linked list class itself, in addition to having a head pointer and a tail pointer, which initially would be set to null, you would have the various operations for inserting or adding a new node to the linked list, or deleting a node from your linked list, finding a particular node in your linked list. So all the operations associated with a linked list would be in that particular class. Alright, so I'm going to go ahead and wrap up this video by just doing a quick summary associated with this linked list structure. So we think of a linked list as simply a sequence of elements called nodes, and we would have some sort of link or pointer here called a head pointer or a head link that gets us to the very first node, and then the way we get to the subsequent nodes is by following these links or these pointers. And at the very end, the very last node here would reference some sort of null value, something to indicate that we're at the end of this list. And the nodes themselves have data. So in our example, we just simply had a name, but we could certainly have a lot more data associated with each node. And not only does it have data associated with it, it has to have a link or a pointer that can reference other nodes, or it can reference the value of null. In terms of the pros and cons associated with a linked list, it's really good at insertions and deletions, so it does that in a constant amount of time. So it doesn't matter how many nodes we have. We could have 50 nodes, or 50,000 or 50 million nodes. In terms of doing the insertion or deletion, we do that in a constant amount of time. So where the linked list is weak is in terms of doing random access. So if we think about a vector or an array, we're able to get to any particular element in a constant amount of time. But with the linked list, that's not the case. It requires a linear amount of time, so it's dependent upon how many nodes we have, how long it takes to get to a particular node. But once we get there, if we need to do insertion or deletion, we can do that in a constant amount of time. So for applications of the linked list, it's used for the underlying data structure of other data structures, so we can make use of a linked list to implement a stack or to implement a queue. There's also some other uses for the linked list associated with some other data structures that we haven't talked about just yet, so I'll probably hold off on that discussion until we actually discuss those other data structures. And it's also used just really anytime we need to have fast insertions or deletions, but random access is less important. Alright, so that's it for this video.